We will continue with our topic on coastal protection. Today we're going to look at breakwaters. There are various types of breakwater design, the purpose of which mainly is to dissipate and reflect the incoming wave energy so that the transmitted wave energy is reduced. We have previously looked at floating breakwater, which is one example of a moor type floating structures, and in today's lecture we are going to focus more on the type of breakwaters which are constructed on the seabed. One of the main example is rubber moon type breakwater, which is made up of different layers of quarry stones, and we will look at the design principles behind this type of breakwater in the subsequent sections. Breakwaters can also be made of concrete structures with vertical face, such as this, or a combination of concrete type crown section resting on a rubber moon type cross section beneath. These figures here shows more close-up views of a different type of breakwaters. Over here we have a composite type breakwater with vertical concrete wall and rubber moon in the lower section. However, we notice that in the head section here, there is no more rubber moon structure, possibly due to displacement after severe storm attack, whereby maintenance or repair work has not been carried out. It is common for breakwaters in the coastal region to be subjected to cyclic damage, and thus the need for maintenance work. This is the typical rubber moon type of breakwater with a crown layer which allows the passage of constructions machinery, so that in the event that the rubber moon units are displaced, then access for maintenance works can be carried out much more easily. There are also breakwaters which is built to be submerged underwater. Main reason for doing that is for aesthetic reason, so that it does not protrude above the sea water surface. However, since the breakwater does not occupy the entire water column, this also means that the wave energy near the water surface can be transmitted to the lee side, and hence the effectiveness of a submerged breakwater is limited. However, submerged breakwater can still reflect partially wave energy that occupies a large proportion of the water column. There are other creative type of breakwater which is also used to promote the growth and thus the health of the ecosystem and the aquatic marine environment, such as the reef ball. If we move further away and look at the layout of the breakwater, we can see that they may be oriented in different ways in order to achieve optimum protection of the shoreline. This is usually located in such a way that it is able to intercept the predominant wave direction that is attacking a particular local area. For example, we can see in the first figure here a detached breakwater which is meant to protect a jetty in this location. Notice that there's no protection on this side, which might mean that the predominant wave energy usually comes from this direction. Over here we have a series of detached offshore breakwater which is designed to protect a long stretch of beach. But in order to allow for passage of water, there are gaps in between the breakwater so that the inner near shore area is not completely cut off. Here we have a very interesting breakwater which is being aligned in such a way, possibly due to the incoming wave direction again, and also to accommodate for the navigation of vessels in this region. More specifically, we notice that here we have a series of breakwater which is constructed and oriented in such a way so that it creates a relatively sheltered inner harbor area in this part that is protected from the wave energy that possibly come from all these different directions during different seasons of the year. By orientating the breakwater in such a way, we expect that the diffraction will cause the wave energy to be greatly reduced by the time it reaches this inner harbor section. We mentioned that breakwater is meant to reflect and dissipate wave energy, as we can see, for example, here, whereby this breakwater effectively reduce the amount of wave energy on the lee side here compared to the sea side here. However, energy may still be transmitted to the lee side by overtopping or direct passage if it is a submerged breakwater, or because of energy which is transmitted through the porosity in the breakwater structure, such as a rubber moon breakwater which is made up of quarry stones. Recall that the wave energy can be written in this form, whereby it is proportional to the square of the wave height and the wavelength. So we can write the total amount of incident wave energy to be equal or larger to the transmitted wave energy plus the reflected wave energy. If we divide the entire expression by L, assuming that the wavelength is a constant, we get this expression. And again, if we divide the entire expression by the square of the incidence wave height, we then get this expression where CT is the transmission coefficient and CR is the reflection coefficient. So the sum of the square of CT and CR will always be less than or equals to 1 due to energy dissipation. If there is no energy loss, then from here we are able to get CT as the square root of 1 minus CR squared. Take note that for deep water wave, typically 70% of the energy is concentrated on the top 20% of the water column, which is why breakwater is very effective in reducing the amount of wave energy on the lee side. Right now, let's focus on rubber moon type of structure, which consists of interior graded layers of stone and an outer armor layer to minimize transmission and to maximize wave energy dissipation. The figure here shows an example of a cross-section of a rubber moon type structure. The interior of the rubber moon structure is made up of graded stones of different size. Typically, the larger size is on its face so that they are able to withstand the attack of the wave, especially on the sea side. which is most likely going to have larger armor unit. Notice also that the crown level on the seaside is higher in order to avoid overtopping if necessary. And at the toe, protection is provided to avoid scuffing and toe failure. The crest usually will be designed wide enough for maintenance machinery access. Rubber mold type structure is a very popular option for breakwater, as we already mentioned, but the same rubber mold structure can also be used for other category of coastal structures, such as jetties, which refers to a pair of shore perpendicular structure, usually designed to provide passage for navigation at a river mouth. Rubber mold structure is also popular to construct groins, which is again perpendicular to the shore and it serves the function to intercept longshore transport. Rubber mold structure may also be used as revetment. That means they are constructed parallel and onshore on the beach itself to protect the shoreline. This figure here shows the typical cross-sectional design of a rubber mold structure. As mentioned, our main interest is to determine the dimension of the structure in order to fulfill the functional requirement, which in this case we must make sure that the crest level is high enough to avoid wave overtopping from the ocean side to the harbor side. The crest level must also be wide enough for vehicular access. The rubber mold structure will be sloped on both sides, but the slope on the seaside typically will be more gentle in order for the armor unit to remain stable under storm attack. The slope on the harbor side, on the other hand, can be steeper due to less energy exposure. For each of the layer, the thickness will also be determined so that there will be a certain number of the quarry stone in each layer to provide sufficient interlocking property. Toe protection will be required, and once these are all determined, we will then get the overall idea of how the cross section look like, the overall size of the entire breakwater, and thus the loading imposed on the seabed to find out whether the bearing capacity of the proposed location is sufficient or not. Based on the cross section as well, we are then able to estimate the total cost of the material required as well as the construction cost. For rubber mold structure used as a revetment, the design is also similar. Cut-off wall may be provided at the toe in order to provide anchoring and thus stability to the sloping riprap or armor unit. Wave run-up deflector may also be provided in order to prevent wave overtopping or run up to the land side of the structure. Most breakwater which is constructed onshore will also be used in conjunction with geotextile to prevent the scouring and loss of the finer sand material from the beach. Some of the common failure mechanisms of breakwaters includes sliding, overturning, slip and tilt, settlement and sliding on the subsoil, subsoil failure, overtopping, and armor instability. It is always preferable to increase the crest level above the mean sea level in order to reduce wave overtopping and energy transmission. Also, by spreading the load of the structure over a larger area can help to prevent the risk of foundation failure. However, both these approaches means that the breakwater is likely to be much larger, and that usually would translate to high construction and initial cost for this particular option. Other design considerations for a breakwater would be scour protection. One is at the tie-in to the shore, such as this breakwater. The tie-in refers to this position where the breakwater is connected to the shore. Since the breakwater is oriented in this direction, we can expect that the predominant wave direction is coming from this direction. It means then that the wave is likely also to attack this section of the shoreline, which exposes it to possible erosion. And as a result of that, the tie-in location must be properly designed to prevent any structural failure. Another aspect of scour protection is at the seaward toe, as we are going to look at in the next slide. The loss of soil in the toe section can cause the breakwater to fail, and that is why toe protection is very important. This example of how the toe can be stabilized from soil loss, and in another case here we have precast armor unit which is protected at the toe by this quarry stone formation. Based on our previous discussion, it may thus be concluded that foundation conditions is one of the most important criteria in rubber moon structure design. This is closely related to the water depth, whereby the larger the water depth, the larger the size of the structure, and thus the more critical the foundation bearing capacity is. In addition, the design considerations will require information of the design wave climate, which includes the design wave height, the predominant wave direction, as well as the duration of attack, which are important to determine the layout, orientation of the breakwater to achieve optimum effect. Another important aspect is the stone availability from nearby area, which will greatly reduce the cost of transportation. Stone characteristic is also very important to achieve the stability of the rubber moon structure. Last but not least is the degree of protection. As we mentioned, rubber moon structure will be subjected to damage. If it is desired that the structure has minimal damage even under the most severe condition, then the armor unit required will be relatively large and thus much more expensive. On the other hand, if small armor units are used, then the degree of protection is lower and the structure is more prone to damage under storm events. So the concept of allowable damage will be adopted in the design, which will be discussed next, and using appropriate safety factor, the rubber moon armor unit size can then be determined accordingly.